Hello, everyone. Today, I would like to introduce our tool MultiABLER. So this is a tool for LCMS analysis on lipidomic and metabolomic data. So I will show a simple demonstration on how to use MultiABLER here. So first, let's load our tidyverse and MultiABLER. Then we will load where our file is being saved. So this is our head directory. I will also read in the sample information and where the MZML file is being stored, as well as read in our MZML files here. So we can see with our console that the sample information contains 3 columns. The first column are the sample names that each ML file corresponding to. The second column is the experimental condition of each sample. And the third column labels whether the ML file is an actual sample or is it a blank control. And if we check in our ML files here, this is all of our list of ML files that we are going to read in using XCMS. XCMS requires 3 parameters in here. So we include peak density parameters, sense wave parameters, and overlap parameters. So we can define our own parameters for XCMS alignment. Users can also just run in the program with only put in the peak density parameters, and we will also provide a default sense wave parameters and overlap parameters. So once we are able to set the parameters, we can start run the XCMS files. Here, I chose not to save the XCMS X data. However, we can easily choose to save the XCMS data and provide where is the safe location. So let's run the XCMS alignment. So now XCMS will start running, and we'll see you after the XCMS is being done. Okay, so XCMS has finished running, and we can see that we have successfully detected all of the chromatographic peaks in our ML files, align them using XCMS algorithm, as well as using camera to annotate all the relevant adducts and ions. So let's clear our console here, and we can actually check the XCMS table, and we can see all of our successfully aligned XCMS feature table. And so let's just write our output here. And so the file is going to be saved with this file path, and we will export this file to LipidFinder to run LipidFinder filtering. While we are at it, let's also run our annotation, because annotation actually takes quite a long time. So let's run our metID annotation using metID annotate. Notice that in metID, we do require the table to name the mass spec, MZ ratio, and our retention time as MZ and RT. So we will just use dplyr to rename our table and run it through metID. So now metID will start to annotate our data. And while we are at it, let's go to LipidFinder and filter our XCMS table using LipidFinder. Okay, so now I'm in my computer's command line or terminal. And this is the only part during the MultiABLER pipeline that we will require external software that is not packaged in the R package, because LipidFinder is only implemented on Python. However, LipidFinder is a very good tool for filtering out the solvent blank, the adducts, as well as the ions and other noise identified in our data. So we would use that as part of our pipeline. So let me just copy the code for the Python. And here I just run Python and run peak filter. So peak filter is our command line for LipidFinder. And we would use the option I to input our exported LipidFinder output from MultiABLER. And then I would put in the parameters, which is also included in our demo data on our GitHub page. And I will save the output in this folder. So now LipidFinder is going to start running. And so let's jump ahead to where LipidFinder is finished. Okay, so in here we can see that LipidFinder has finished its process. So now we can import the LipidFinder result back into our console. Okay, we are back into our console, and we can see in here the annotation has been done already. So let's clear the console up and we'll read in our LipidFinder output. So now we can start processing our data with our filtering step in here. So first, we will join all the LipidFinder output. Here in our example, I've only used one profile. However, we can easily use diverse bind rows to join multiple data frame and manipulate them together. Now we will start separating the feature information, so the MZ ratio from the feature table. And finally, we can start modifying our table by first performing filtering. So in here, we can do a quick comparison. Our feature table was originally read from LipidFinder, and you can see that this labels with what omic it is, which polarity mode was it analyzed on. This is our original feature ID, and these are our samples reading abundance that has been normalized by LipidFinder. But after our filtering and transformation step, the data frame will be reduced into a log transform and imputed form here. So now we are ready to run the eigenMS normalization. First, we will identify the eigenMS sample information. So in particular, we will filter the sample that are only labeled as tissue sample, and we will rename the column condition into group. This helps the function to identify which group do we use for the normalization. So after that, we can input our manly.df data into norm eigenMS for normalization. So here eigenMS starts running, and we'll see you after eigenMS is finished. Okay, so now eigenMS has finished running. So we can see in here, we got our eigenMS data frame in here. So now we will run median normalization on the eigenMS data frame. And finally, we will annotate our current feature table with our previously annotated annotation features using the HMDB ID. So this step will help us to identify for each unique HMDB ID in our dataset, identify the best features that represents that HMDB ID metabolites. So now that the script has finished running, we can check we resulted in a unique HMDB ID for each features and a normalized result using eigenMS and median normalization. All the scripts in here are available in our tutorial page as well. Thank you for watching this tutorial video.